Hello, we are Team 24022, and our project was to design a new tread plate pattern that uses a CNC turret press manufacturing method. Our sponsors are Eric Knowles and Lloyd Becker from Caterpillar Inc., and our mentor was Mike Majerick of the University of Arizona. Now, what is a tread plate? A tread plate is a walking surface that has a pattern of protrusions that increases the coefficient of friction between a worker's boots and the surface that they are walking on, thus ensuring a safe operating environment. A CNC turret press is a machine capable of stamping a pattern out of the material placed onto it using a die, producing tread plates much more efficiently than other methods. The product that we have designed is primarily utilized on hydraulic mining shovels, which work to provide humanity with the raw materials needed to support an ever-expanding and improving civilization. Now, the current state-of-the-art that Caterpillar Inc. uses are a weld-on stud tread plate, which currently provides the best coefficient of friction, and a star punch tread plate, which uses the CNC turret press manufacturing method. What we have done is design a tread plate that has a high level of friction that can be manufactured using a CNC turret press. Hello, my name is Stephen Gonda. I'm an engineering management major, and I am the team lead.
Hi, I'm Natien Din. I'm a mechanical engineering major, and I am the mechanical design lead for this project.
Hi, I'm Jackson Cobb. I'm a mechanical engineering major, and I'm the analysis lead for this project.
Hello, I am Abdullah Al-Mutairi, and I am an industrial engineering major, and I'm the safety lead.
Hello, I'm Abdulaziz Al-Shaya. I'm an industrial engineering major, and I am the documentation lead.
My name is Brian Prevey. I'm a mechanical engineering major, and I'm the project procurement lead. There are certain requirements that needed to be met in our project. We organized them into 4 sections: performance, manufacturing, geometric design, and testing. Notable requirements to our project include our tread plate must meet stress and design targets as mentioned in ISO 2867. Our tread plate must meet Caterpillar's specified frequency and stress design targets. Our plate must have a coefficient of friction that is greater than or equal to the weld-on stud design, and our tread plate must be manufacturable via a CNC turret press process.
In this project, 3D modeling was used to create the tread plate designs the team came up with. We utilized SOLIDWORKS 3D modeling along with the sheet metal forming tool in order to do this. Modeling our designs not only allowed us to create a visual of our tread plates, but also gave us the opportunity to 3D print these models as well, which was the backbone of our testing methodology. This rapid prototyping approach allowed us to immediately test any new designs and design modifications we came up with. 3 tests were performed for this project: a tread pattern spacing test, friction test, and a traction test. The first test we performed was the tread pattern spacing test. The goal of this test was to determine the most optimal tread pattern spacing for our designs. We 3D printed 4 copies of 2 of our concept tread plate designs, with spacings of 50 mil, 75 mil, 100 mil, and 100 mil with a 50 mil diagonal offset. This test was performed by clamping down the tread plate while pulling a weight mount across the tread plate using a linear actuator. A force gauge will then collect the data needed to calculate the coefficient of friction for each plate. The spacing that we found yielded the highest coefficient of friction was the 100 mil with a 50 mil diagonal offset. Moving forward, we will only be testing designs with this spacing. The next test performed was the friction test. The purpose of this test was to determine the coefficient of friction provided by each design for the purpose of comparing to Caterpillar's weld-on stud plate. This test will be similar in procedure to our optimal spacing test, but the purpose is solely to find the best tread pattern in terms of friction provided, not to determine the best spacing, as that's already been tested for. The results of these tests will be compared to our baseline results to ensure that the project requirements are met. From this test, we found that the triangle tread pattern design was the most optimal, so we created 2 more designs similar to it and tested those as well. The final test we performed was the traction test. The purpose of this test is to add another factor to take into account when deciding the best tread pattern design. That factor is the feel of the tread pattern. Part of our project is subjective, in that the tread plate should make one feel secure and planted when walking or standing on the surface. So to perform this test, we used 2 work boots commonly worn on hydraulic mining shovels. Boot 1 is a metatarsal anti-slip steel toe worn by me, and boot 2 is a hard-bottom steel toe boot worn by Jackson. The basic procedure for this test is to have one foot hold down the tread plate, then using the other foot with the boot on it to shuffle forwards and backwards, then rotate or swivel. A value will then be recorded for the traction felt when doing the previous 2 movements, where a value of 1 corresponds to low traction or grip, and a value of 10 corresponds to a high level of traction or grip. These scores are then factored into the final design Q matrix.
Let's now look at the modeling and analysis performed for this project. As mentioned earlier, 3D modeling and 3D printing allowed us to rapidly prototype and test our designs, but it wasn't just limited to testing. We also used 3D modeling in order to set up the analysis that would need to be performed on our designs. And to do this, we created a model of a tread plate support similar to what would be seen on one of Caterpillar's real mining machines. For the analysis in this project, we made use of finite element analysis in order to verify that we met both the engineering standards discussed previously and the stress and frequency requirements given to us by Caterpillar. To achieve this, we used both structural and modal finite element analysis. Structural FEA was done to verify that our designs met both loading cases of ISO 2867 and that our design met the displacement and G-load requirements given to us by Caterpillar. The purpose of the displacement requirement was to ensure that the plate did not deform elastically greater than a specified amount while under the ISO 2867 loads, and the purpose of the G-load requirement was to ensure that the tread plate we design does not experience any large or abnormal stresses under normal gravitational loads that could decrease the life expectancy of the product. Modal analysis was used to verify that our design met the frequency requirements that were also given to us by Caterpillar. The purpose of this requirement was to ensure that the natural frequencies of our design did not coincide with the induced vibrations of the machine under normal operation or fall below a certain specified frequency. After performing these 3 analyses on our top 4 tread plates, it was confirmed that our final designs met all stress, displacement, modal, and G-load requirements. After designing and testing various tread patterns, we used a quality function deployment form provided by Caterpillar to aid in weighting the various design factors. This allowed us to pick the best design to manufacture from our top 4 tread patterns. And as we can see from our P matrix, design 240227 had the best overall score, so it is the design that we decided to move forward with for manufacturing.
After selecting our best design to manufacture in steel, a last-minute crisis occurred. The original manufacturer we intended to work with ended up not replying to us in a timely manner after we've selected our final tread plate to be created. They were going to be the ones making the tooling required to create our tread pattern, and with 5 weeks left until design day, we needed another way to get that plate made. We found a new manufacturer that was willing to help us create the tooling, but that left us to designing the tooling ourselves. With no prior experience with sheet metal bending, we began working with our sponsor and researching how to model sheet metal bending and the proper tooling needed to create our tread pattern design. We discussed with our sponsors and decided on designing a punch and die tooling that can be used in a hydraulic press to punch a pre-cut sheet of steel to form our tread patterns. Although this is slightly different than our original plan of a manufacturer using a turret press, we feel that this concept of using a punch and die tool can be applied to a CNC turret press.
So, does the design meet the requirements? Our top design, 240227, the tri-triangle, has exceeded the performance requirements set by the Caterpillar well-done stud tread plate. Our plastic design performs 27% better than the plastic well-done stud sample provided by Caterpillar Inc., and the results of all of our 3D printed samples is shown here. All of these tests were performed in a dry environment, and then when we tested our steel sample of 240227 against the steel sample of the well-done stud tread plate in muddy, dry, and oily environments, the muddy environment is a 3-to-1 ratio of dirt to water mixture by volume, and the oil used is 10-weight or ISO 32 standard hydraulic oil. The results are also shown here. As you can see, our tread plate performs better by 39% in dry conditions, 24% in muddy conditions, and 7% in oily conditions.
We are Team 24022, and thanks for watching.